Alright, welcome back to the continuation of the workshop videos. So we're looking to kind of round that out today. So what we've got is just a little bit of presentation material that we're continuing. Last time we just looked at undo, so this time we're just looking at seeing if we can pull together our subtotalers for these. So on this particular case, I'm just doing our angle. So we look at the angle as our right angle. So we're looking for theta. So it's opposite. So opposite over adjacent. There's our hypotenuse, which we don't know. So the most convenient one is to use tan. So tan theta will be equal to 5 over 8. So therefore theta will be equal to, taking tan to the minus 1 of both sides, will be arctan or tan to the minus 1 or inverse tan 5 over 8. And so we put that through our calculator and it approximates to 32 degrees. Okay, for these right angle triangles, we're told in the question that they're right angle triangles, so we can keep using that idea. Just looking at it from this angle, this time we've got a hypotenuse and we've got an opposite. So this one will be sine of theta will be equal to 7 over 9. Opposite over hypotenuse. So, okay, this one was TOA. So sine, now taking the inverse of the sine, or the arc side, what you do to one side, you do to the other. So we'll end up with theta will be equal to the arc sine of 7 over 9. So we put 7 over 9 in the calculator, and we'll get 51.1 degrees after rounding. Okay. So pretty straightforward again. Just check your angles. Check your sides. We've got an adjacent and a hypotenuse. And a hypotenuse, that's an opposite. So we've got a adjacent over hypotenuse. Because theta equals adjacent over hypotenuse. Taking arc cos or cos to the minus 1. We'll undo. So cos to the minus 1, 4 over 11. So therefore theta, because undo, is equal to cos to the minus 1 or arc cos, 4 over 11. Put in your calculator a second function if that's what it's got. And it should approximate to 68.7 degrees, making sure your calculator is in, of course, in degrees. Alright, so find Pythagoras theorem. Well, we've been doing this ad nauseum, but I promised in the video that I would do that. So the hypotenuse is equal to the sum of the other sides, the siblings, if you want to look at it that way. Okay, then we undo. What you do to one side, you do to the other. The undo of x squared is simply x. And we get 8 eighths of 64 and 36, which is the square root of 100, which is equal to 10. So x is equal to 10. Now we could notice any factors of that and divide by 2, for example. 3, 4, 5, is that right? If we divide it by 2, we'd get 3, 4, 5. You could have done that without so much of a thing, but if you divide it by 2, you'd have to double it again, so that would be 10. Okay, so 3, 4, 5. Alright, so lovely thing here, hypotenuse, y squared, is going to be equal to the sum of the other squares So undo both sides. We'll get y is equal to the square root of 25 plus 144, which is the square root of 961. Now you get used to these. If you're doing your homework, you'll get used to seeing them. So 169, I know it's 13. So that one's 13. No 3, 4, 5 proportions there. Okay. So same again. Now this is designed to trick you. So you need to recognise that 7 squared, which is why I've been doing it, is equal in this case to the sum of the other sides. See that? Be careful, please. Okay, so we're going to have to minus the 2 squared. This is more like what we've been doing. So x squared will be equal to 7 squared minus 2 squared. Taking the square root of both sides, x will be equal to the square root of 49 minus 4, which is the square root of 45. Now we can play with this a little bit. It's the square root of the product of 5 and 9. Okay, and that can be rewritten as the square root of 9 times the square root of 5. So that's just your algebraic gymnastics happening. Square root of 9 is 3. 3 root 5. Okay, now we could have done the square root of 45. Okay, but we've got an exact value that's been reduced or simplified. That's our exact value. Not exact value is trig, but nevertheless an exact value. And a decimal for that would be 6.7. So that's an approximation. So algebraic exact values and exact values trig are slightly different. So we don't want to lose sight of that. Okay. All right, so the next thing we'll consider is the similar triangles. So it's just proportions being the same. If you've not done them before, it's not terribly difficult. So any two right angle triangles that include an angle are similar. Okay, similarity means that their proportions are different, but their basic angles are the same. Okay, because this says corresponding angles. So the gist of the thing is that the proportions, same shape, but proportions are different, same angle. So we can use a rule. This is, for me, a de-emphasised topic as far as the other thing goes. So if we draw this as a cos, so we just construct some kind of right angle triangle. Okay, and think about the proportional sizes. Cos is k, adjacent over hypotenuse. So the hypotenuse is 13, and the adjacent is 5. So according to this, I could put my 5 here because it's the shorter side, and I could put my angle here, and this would be my unknown. So that would be reasonable. And Pythagoras defined the missing side, so 13 squared is equal to the sum of the other two. Okay, so we can minus 5 squared from both sides. So x squared is equal to 13 squared minus 5 squared, which now tells us to take the square root of both sides. So x is equal to the square root of 13 squared, which we worked out was 169. Minus 25. And that's 4, and that's 4, so it's the square root of 144. You just get to know them. You can use your calculator, it doesn't matter. And that's 12, so x is our 12. So there it is, we'll put it in as x equals 12. You can do it any way you like, but just as long as you get the correct things. Now, TOA is opposite over adjacent, 12 over 5. So tan theta is equal to 12 over 5. Okay? So that's fairly straightforward. Okay? All right, so when looking at the similar triangles, you'll get to use some rules, but we'll get to those in a little while. All right, now what's this? Cosec and sec. Now sec and cos go together. always remember that just by looking at that. But cosec and sine go together. Okay? So cosec is the reciprocal of sine. Okay? Sine itself was 1 over 3. So it'll be 1 divided by 1 over 3, which is 1 divided by 1 over 3, which is 1 times 3 over 1, which is just 3. Okay, so just doing this little bit of menagerie here, I could have just written 3, but then you would have to do this in your head. Okay? 1 over 1 over 3. Alright, so just trying to be helpful there. Okay? Now, if tan theta equals 2, now what's in your mind's eye? How would we normally write? We wouldn't write 2, but in this case we are going to write it as tan theta is equal to 2 over 1. We're going to introduce that one because it suits us. Now tan is TOA, opposite over adjacent. Okay, so when we do our triangle, what we'll have is an unknown. Right, TOA, opposite over adjacent, unknown. Okay, so in this case here, x squared is going to be equal to 2 squared plus 1 squared. X squared, take the square roots of both of those. X will be equal to the square root of 4 plus 1, which is 5. Square root of 5. Okay. So sine theta now is SOP, opposite over hypotenuse, and we just said that was root 5. So opposite 2 over root 5. So some pretty de-emphasised stuff for you to process there. I'm sorry to use language like that, but it's important that you know the difference. Okay? Alright, now magic triangles. This is the big sheet. I'm sorry, but this is more important than a simple name like magic triangles. This is our important and helpful exact values trig. Okay, this is the sheet that I've been banging on for weeks. Okay, this is the answer. It's because it's about doing this by sight. Okay, it's about doing this by sight. What's this one asking? This one's asking the length of y at 30 degrees. The length of y 30 degrees. There it is. That's a half. That comes from our exact values trig. I'm not going to draw it. I'm not going to draw it because it's elsewhere. Okay? Weeks and weeks and weeks I've been doing it. I need you to know it. Look it up. Okay? So that's a half. What's the long side at 30 degrees? Root 3 on 2. Root 3 on 2, opposite TOA. Opposite over adjacent. Half over. Half over. Root 3 on 2 is a half divide root 3 on 2, which is a half times 2 on root 3. They're cancelling. 1 on root 3. That's 10. Sine 60. There's sine 60. I'll do a new triangle for you. Diminishing triangles. There it is. If you don't know what I'm talking about, whoops. Root 3 on 2 now is up here. The short side's here. So the sine is root 3 on 2. That's the y value. The cos is the short side, half. Root 3 on 2, opposite over adjacent. Okay, so those things are not so important. For this one here, our version of this, the one that I've been using, looks like this, 1 on root 2. So this means this has been scaled. To get this size, it's been multiplied by root 2. So what do you think this one is? 1 times, this is root 2. We don't even have to think about it. And because they're the same size, we know the angle is pi on 4. It's the same angle, pi on 4, similar triangles. It's been scaled, okay? So for this particular example, the sine of 45 is going to be opposite 1 over root 2. Oh no! 1 over root 2 over 1. So either way, it's 1 over root 2. 1 over root 2. In this case, the TOA is 1 over root 2 over 1 over root 2, which is 1 over root 2 divided by 1 over root 2, which is equal to 1 over root 2 times root 2 over 1. Oops, cancelling 1. So the tan 45 has a unique set of ideas. Look, if that's been a little bit lost on you, I've been at it for weeks and weeks and weeks, trying to get you guys to understand how important this is and trying to get you to recognise these things. Okay? Now, the only other thing I would say about this is when you've got a 1 over root 2, you can rationalise the denominator, which takes the root away. And so that's a root 2 squared, so you get a 2. So it's the same form. That's the same form as this one here. Okay? So some lecturers like to write it like that. Alright, I can't do much more with the exact values trick if you haven't been paying attention, which is why I'm pausing now. Alright, we can use the sine and cosine rules to help us develop a response to triangles of a similar type. Just notice the form. This is emphasised quite heavily at school, but it's not something I want to be over the top about. Let's just do some examples, and we can work with that. All right. So in this case here, just follow your convention. Just make sure that you follow your convention. Okay. So for this one, 10. Oh, need to turn the pen on. Haven't done that. Oops. So what I'll do is it's 20 minutes, so I'm going to stop here and come back in a minute and do this one. All right, back soon.